Hi everybody, welcome to another video in differential equations, section 7.5, solving initial value problem. So we spent 3 sections in this chapter talking about Laplace transform and then the inverse Laplace transform, and then we go to the question, what that has to do with differential equation? Well, we're going to answer that question here. Right, so bottom line is it is still differential equation, and we still just solving differential equation, in particular initial value problem. Right, so the step to solve an initial value problem is first we'll take the Laplace transform from both sides, so we turn a differential equation into an algebraic equation, and that is the point. Remember when the first question we raised when we studied Laplace transform, we said what does that have to do with differential equation? Well, when we use Laplace transform, we can turn a differential equation into an algebraic equation, meaning that we don't have to use calculus to solve for the equation. So from Laplace transform, turn that into an algebraic equation, and from there we can solve the equation algebraically. So this should be easy. This step should be easy. Yeah. And then finally we use the inverse transform to transform back to the equation. So we have the equation, do the Laplace transform, solve the equation, and then inverse Laplace transform. Right, so let's look at the first example. It's very simple, linear first order equation, initial value problem. So first we'll transform both sides, transform the left hand side, transform of the derivative. The formula is over there. So derivative, and then transform of 3y. So transform of the derivative is going to be this, and that's where we need the initial value for. That will be 6. And then transform of the function from t to s, so that's easy. And then transform of 13 sine of 2t, transform of sine. Sine is an odd function, transform will be an even function, of course. Transform of sine, it's going to be that. So in this case, b is 2, so we have 2 over s squared plus 2 squared, and that's what we have. Right, transform of the function is just going to be y of s, and transform of 13 sine of 2s is that. So from the equation, we do the Laplace transform and we turn this into an equation. Now, both of these have y of s, so we factor it out. So we have s plus 3, and y of 0 is 6. So that's why we have the left hand side. On the right hand side, 13 times 2, that's 26 over s squared plus 4. So now we just have an equation, an algebraic equation, so we don't need any calculus here to solve for the equation. And to solve for y of s, we just going to divide plus with plus 6 on both sides, and then divide by s plus 3, common denominator, and then multiply by s plus 3, we have 26 plus 6x squared plus 24. So we just simplify this into one big fraction, and we have that. Finally, we just need to find the inverse Laplace transform. So in the using initial value, using Laplace transform to solve initial value problem, there will be 3 steps. First, we'll take the Laplace transform. Second, we solve for y of s, and finally we use the inverse Laplace transform. And now we know y of s is equal to this. We just need to decompose them, and decompose them we use the previous section partial fraction, and we decompose that function into this. So finally we can say y sub s is equal to negative 2s plus 6 over s squared plus 4 plus 8 over s plus 3 after we do the partial fraction. And then finally we do the inverse transform of that. So inverse transform of this negative 2s, and then we split. Remember, the inverse transform of sine of bt is still over there, right? So we need this 2 to be the same as this constant 2. So that's why we need the 2. So we split the negative 2s, and then we split 6. But we're going to need 2 on the top. So we put 2 on the top, and then we have 3. 3 times 2 is 6. Instead of 6, we have 3 and then 2. The reason we put 2 on the top, so the 2 here will match. And finally, Laplace transform of s over s squared plus 2s, s squared plus 2 squared, that is cosine 2t. Laplace transform of this is sine 2t, and Laplace transform of this is e to negative 3t. Right. So take the Laplace transform, solve for the function, and take the inverse Laplace transform. Of course, in that process, you don't see that any step that we have to use any calculus, but we have to use the Laplace transform, which of course itself is a calculus problem. Right. So let's look at an example. I've solved this initial value problem. So the first step, of course, find the Laplace transform. So take Laplace transform. So we apply Laplace transform on both sides. Right. Now, by linearity of Laplace transform, we split this. We have Laplace transform of second derivative minus 2 Laplace transform of the derivative plus 5 times Laplace transform of the function equal to negative 8 Laplace transform of e to negative t. Right. Now, transform of the second derivative and the derivative, we're going to use that. So first transform of the second derivative is going to be s squared transform of the function minus s y naught, and then minus s. So we notice that if it's a second derivative, so we start with the second degree, first degree, and then 0 degree, which is s to the 0 power. But in that case, the function should go from to transform y and then the derivative. Right. And then we have minus 2. Now transform of the derivative. This is the first order. So we'll have s, y of s minus y 0. Right. Of course, the formula over there. And then the transform of the function 5y, and then negative 8. Transform of e to negative t is 1 over s plus 1 Of course, I don't require you to memorize the Laplace transform table. You should have that with you when taking the test. And when we take in the final, you will have the formula for all of those Laplace transform. Anyway, let's just simplify this. We have s squared y sub s minus s. Initial values at 0 is 2, so we have minus 2s minus the derivative 2 times s y sub s minus 2 y naught is 2, so minus 2 times minus 2 is plus 4, then plus 5 y sub s, and we have negative 8 over s plus 1. Right, so now we solve for y sub s. That's the second step. Right, now we factor out y sub s. We're left with s squared minus 2s plus 5. Right, now what's left, we can move to the other side, so we have negative 2s. Let's add 2s on both sides, and here we have minus 12 plus 4, that is minus 8, right? So let's plus 8 on both sides. So that 2s cancel out, and negative 12 plus 4 and 8 cancel out. So we have 2s plus 8 minus 8 over s plus 1. Right? Of course, finally, we just divide by s squared minus 2s plus 5 on both sides. So y sub s equal to 2s plus 8 over s squared minus 2s plus 5, and then minus 8 s plus 1 s squared minus 2s plus 5. Right, common denominator, we just need to multiply s plus 1 on the top of this. So I multiply top and bottom by s plus 1 to have the common denominator. Right. Common denominator. Right, 2s squared plus 2s plus as, that's plus 10s, 2 and 8, 10s, then plus 8 minus 8. Well, of course, a and a cancel out, so we have 2s squared plus 10s over this s squared minus 2s plus 5. Right. So as you see, we use Laplace transform, and then we solve for y of s. There's no calculus needed, it's just algebra. Right, the next step is, of course, now we have y of s, we take the inverse Laplace transform to get back to the function, and that's what we get the solution. Number 3, we apply inverse Laplace transform. Right. So since y of s equal to that, so we have y of t will be inverse Laplace transform of y of s, which is inverse Laplace transform of that. Right? So Laplace transform, and then solve for the equation algebraically, and then have the Laplace transform. Right. To save time, we actually did this in the previous section, section 7.4, the last example. So we find the inverse Laplace transform of that. You can just go to the previous video or your previous note. When we use the partial fraction decomposition, so we use partial fraction to decompose this into those two, and then we apply the Laplace transform to that. We turn into this. So I'm just going to write the answer is negative e to negative t. I just want to write e to the t 3 cosine of 2t plus 4 sine of 2t. So that's all we do. Right? Actually, the problem could be a lot longer, but I just don't want to make this video longer than it needs to. So just focus on the problem. It's initial value problem where we do Laplace transform, turn that into an algebraic equation where we solve for that, and then apply the inverse Laplace transform. And you see, the way we do that is completely what we have, different than what we have before, where we have to solve for the complementary solution, and then we guess the particular solution, and then do the undetermined coefficient. We don't have to do any of that. When we do this, we solve for the coefficient already. We don't have to solve for the constant. Yeah, of course, a complete problem will take a lot of time, mostly to solve for that, but even more work is where we have to decompose a partial fraction. Right, so that is the Laplace transform, using Laplace transform to solve initial value problem. And then you say, what happens if the initial value is not at 0? Well, one thing to note that the formula that we use here only works. This formula only works for initial values at 0. If it is something else, then we have to do something else. Right. Now let's look at the second example. Now, so this equation, I put that W in for a reason. Now the condition, initial condition, is not a 0 anymore. It is pi. Right. So first thing, because I just mentioned that in order to find the Laplace transform of a derivative, meaning find the Laplace transform of the derivative, we need the initial condition at t equal to 0. That is very important. So we have to convert this problem into at time t equal to 0. Right, so how do we do that? Right, so first let y of t equal to w plus equal to t plus pi. And they'll say, why do we have the plus pi? Well, the plus pi is equal to this pi, so plus pi. So when we take derivative, using the chain rule, derivative of the function, and then derivative of t plus pi, which is 1. So that's why we derivative are equal. Second derivative will be equal to that. Now, if you put 0 in for t, we have y of 0 equal to 2. Y naught of 0, put 0 in for t, we have 12. Right? So the initial condition here turn into this initial condition here. Which is good. So we just replace y of t equal to w of t plus whatever that value is at. Now replace t by t plus pi into the original equation. Right? Because if this equation works for t, we can just replace t plus pi. So t plus pi here, t plus pi here, t plus pi here, and t plus pi here for t. Do all of that. And then t plus pi, that is going to be second derivative in terms of t. And then t plus pi, that is the derivative. And that is the function. So we turn this equation into this equation. So if we're going to use Laplace transform, we have to write the equation in terms of t. And the initial condition has to be at 0. So we can do the Laplace transform of derivative, the formula of course over there. Right. Now, just like this problem is exactly the previous problem that we did. So we can write y of t is equal to the solution. We're just going to write the solution. Of course, I shuffle the 3 cosine of 2t, 4 e to the t sine of 2t, and then negative e to negative t. Right. So we have y of t. But the problem is we're not showing for that, we show for w. So we have to replace. So w of t plus pi is equal to y of t equal to that. Right? Because that's what we said. W of t plus pi is equal to y of t. Now that's what we have. Now, if we replace this by x, and then so t is equal to x minus pi, and then we will substitute x minus pi into t in this equation. After we do that, we substitute this back into the equation. So what do we have? W of t plus pi is going to be x. 3e of x minus pi, because that we substitute in for t, substitute in for t, substitute in for t, substitute in for t. That's what we have. Right. Actually, that is the solution. But if we want to, we can write the equation in terms of t. Now just change back into t. 3e to the t minus pi cosine of 2x minus 2 pi plus 4. I mean, there's no more x, there's just t. For e to the t minus pi sine of 2t minus 2 pi minus e minus t minus pi. Of course, we can use the sum, sign of a sum, or sign of the difference. But of course, we can just simplify that, but just going to leave the answer in that form. Of course, we can use the sum of different identity to simplify this, but that's what we have. So the point is still the same. Laplace transform, solve for y of s, and then inverse Laplace transform. The only problem here is this is not in terms of 0. the initial condition is not at 0, so we have to turn the pi into 0. In that case, we let y of t equal to t plus whatever that number is, and we go from there. Right. Next, let's look at this problem. Solve for the initial value problem. Right, that. So the first step is, of course, apply the Laplace transform. First step, of course, take Laplace transform. Right. So Laplace transform on both sides. Good thing is this is the initial condition is 0, so we don't have to do the change variable here. Right. Now the linearity of Laplace transform, so we can split. Right. Laplace transform of the second derivative. S squared, that second derivative, we start with s squared, y sub s, subtract s, little y at 0, subtract derivative at 0. So that is a Laplace transform of the second derivative. Minus 3. Now Laplace transform of the derivative would be s y sub s minus y naught, y at 0, and then plus 2 times y sub s, Laplace transform of y, and then e to negative 4t is 1 over s minus 4. Or s plus 4, of course, Laplace transform of e to the at. I mean here. Right. Now let's simplify this a little bit. S squared y sub s. Initial condition at 0 is 1. Minus the derivative at 0 is 5, minus 3s y sub s. Our initial condition at 0 is 1, minus 3 times minus 1 is plus 3. Right. So that is the first step. We find the Laplace transform. Second step is to solve for y sub s. So y sub s, that's what we solve for. Let's factor it out. So we factor y sub s, we have s squared minus 3s plus 2. Right. And then we solve for y sub s. Here the minus s, we can add that to the other side. Minus 5 plus 3, so that is minus 2. So we're going to plus 2 on both sides. So the s cancel the negative 5 and plus 3 cancel out. On the other side, we will have 1 over s plus 4, and then plus s plus 2. Right, now we just need to divide this on the other side, and we have y sub s. S plus 4 s squared minus 3s plus 2 plus s plus 2 over s squared minus 3s plus 2. Right, now common denominator, we would multiply s plus 4 top and bottom. Right. And so the common denominator of s squared minus 3s plus 2, we have s plus 4. Right, then we have 1 plus s plus 2 times s plus 4, s squared plus 4s plus 2s plus 6s plus 8. So combine the top, we have s squared plus 6s plus 9. Even though this we can factor, but we don't, because what we do next is partial fraction. Right, so Laplace transform and then solve for it, and then after that, of course, we're going to take the inverse Laplace transform and we'll get back to the function. And so that pretty much that's all we do. By the way, this problem I write the solution here, so we should get that. Right. So this section and the next section, some problem will take a lot of time, and so to save, I don't want to make the video extra long. So in that case, we might have some step that we did before, like the last problem, the last two problems. Next, we apply the inverse Laplace transform. So y of t would be the inverse Laplace transform of y sub s, and this will be the curly bracket. Which is Laplace inverse Laplace transform of that. Right. Now, it's easy. Next, we just need to do a partial fraction of that. So partial fraction. By the way, the s squared minus 3s plus 2, if we decompose, I mean just factor, that should be s minus 1 and s minus 2. So I will write down s squared minus 3s plus 2 is s minus 1 times s minus 2 because before we do the partial fraction, we have to make sure that all the factors are irreducible. By irreducible, we mean we cannot factor anymore, and clearly this one we can factor out further. So that's what we have. Right, now let's write. We have s squared plus 6s plus 9 over these two, s minus 1, s minus 2, and s plus 4. Right, so now we know that is all the factors out to the lowest. We cannot break this down any further because that's up to the linear factor already. So here we have 3 factors at the bottom, meaning that we're going to have 3 fraction, s minus 1, s minus 2, s plus 4. Well, this is leading factor. This one will actually we do this in 2 different ways. Right, first, because we have to eliminate all the denominator, so multiply both sides by the least common denominator, which is this, s minus 1, s minus 2, and s plus 4. Right, so that cancels out. We have s squared plus 6s plus 9 equal to a s minus 1 we cancel out. We have s minus 2, s plus 4 plus b. The s minus 2 cancel out, s minus 1, s plus 4, then plus c, s minus 1, s minus 2. Right, now we just need to solve for a, b, c. There are 2 ways to do this. First, of course, the normal way when things complicated, just multiply it out, combine like terms, and solve for that. And I'll use a calculator to do the reduced row echelon form to solve the linear system of equation. Right, so let's do that here. Just multiply this out. A s squared plus 4s minus 2s, so that plus 2s minus 8. Right, 4s minus 2s, that 2 minus 8, plus b, s squared 4s minus s, that's plus 3s, minus 4, and plus c, s squared minus 2s minus s minus 3s plus 2. Right, I'll just combine like terms. Actually, because you can multiply it out, combine like terms. Actually, in the next section, I think, or previously we did something like this. So let's look at on s squared. How many s squared do we have? S squared, s squared, and s squared. So if we factor s squared out, we just have 8 plus b plus c and s squared. Of course, we can multiply it out and combine like terms. We don't need to if we organize things well. Next, we have 2s, 3s, and minus 3s, right? So factor out s. Factor out s. We have 2s, but there's with an a, so we have 2a. There are 3s, but with the b. And then minus 3 but with a c. And finally, just multiply everything out. We have the constant term minus a minus 4b plus 2c. And on the left hand side we have s squared plus 6s plus 9. Right. Now, matching the coefficient on s squared with that, so the coefficient is 1, so the first equation is a plus b plus c equal to 1. Next, we have that with 6s, so the second equation is 2a plus 3b minus 3c equal to 6. And the last equation, of course, that must be equal to 9. Negative 8a minus 4b plus 2c equal to 9. So this is the system of equation. I'll put that in the matrix 1, 1, 1. You can go back to the previous section if you want to see how do we use the calculator to do this. Right, so let us move the calculator here so it's bigger. Right, so that is the matrix. So first, second matrix, I will reduce row echelon form first, and then I will apply to a matrix alpha zoom. If your calculator cannot do this, then we have to store the matrix first. Of course, I did that in the previous section too. Right, I actually do that now too. 1, 1, 1, 1, 2, 3, negative 3, 6. Notice that when you enter the negative, it should be this negative. And apply that, and then turn this into fraction. So 1, 0, 0, 0, 1, 0, 0, 0, 1. We should have the identity matrix on the left, and then negative 16 over 25, 25 over 6, 1 over 30. So that is A, B, and C. Sorry, I have to calculate on the way. Right. So I copy that matrix, identity matrix on the left, and then A, B, and C. Right, with that, we substitute back in here. So y sub s, actually all this, we can decompose into A, negative 16 over 25 of s minus 1 plus B, 25 over 6 s minus 2, and C, 1 over 30 s plus 4. Right, so that is y sub s, and then of course we can now apply the Laplace transform, and y of t will be Laplace transform of this. I mean the inverse Laplace transform of that. And then we can just split this out because the inverse Laplace transform is also a linear. So a linear operator, negative 26 over 25. And we just have 1 over s minus 1. And then 25 over 6. Inverse Laplace transform of 1 over s minus 2. 1 over 30 inverse Laplace transform of 1 over s plus 4. And now that is easy. This is inverse Laplace transform of that is e to the t plus 25 over 6 e to the 2t and 1 over 30 e to negative 4t. Of course, that's just the Laplace transform. That. Right, so by the way, let's just quickly, if your calculator cannot do this, meaning that we have to store the matrix. So second matrix, go to edit, let's store this into matrix B. So go down to B, when edit B, and then enter the values. This is 3 rows, 4 columns. In this environment, we will use the enter button, and then the matrix 1, enter 1, 1, 1, 1, 2, 3, still negative 3, 6, negative 8, negative 4, 2, and 9. Right. So when we go to second matrix, go here to edit, the third tab to edit. If we want under names, hit enter. So that is the matrix A. Now we go to the matrix B, go down to B, and that's what we have. Oh, this is 1, not 11. So make sure go back. This should be 1. Right. So good thing we check. Now back to matrix B. 1, 1, 1, 1, 2, 3, negative 3, 6, negative 8, negative 4, 2. Okay. Now we still apply the reduced row echelon form to second matrix B. Go down to B, and then change to fraction. Right. So we have the same thing. By the way, that is like exactly like the answer we should have. Right. So, and I did mention that this problem, it is simple enough. We should be able to do this by hand without using the calculator. Right. Now let's focus on this equation. Sorry, not that equation. This equation. Right. Now focus on this. Now this is another way to solve the undetermined coefficient. Now, we need to solve for A, B, or C. Think about this. We have s minus 2, s plus 4, s minus 1, s plus 4, s minus 1, s minus 2. Now, if s equal to 1, s minus 1 here equal to 0, s minus 1 here equal to 0. So we don't have those two terms, right? And we just have A left. So that's why I said when we have the linear factor, we can simplify a lot. It can simplify a lot by we just choose something. Like if we want A, we're going to choose s equal to 1 because both factors have s equal to s minus 1. So first, if we choose s equal to 1, in that case, put that in the left hand side. 1 square plus 6 times 1 plus 9 equal to a 1 minus 2, 1 plus 4. Right, the first one I will write everything. Then plus b 1 minus 1, 1 plus 4. So we put 1 in for s. And then c 1 minus 1, 1 minus 2. But we have 1 minus 1, that go to 0, 1 minus 1, that go to 0. So we only have here, which is 1, 6, and 9, so that is 16. And then we have a, that is minus 1 times 5. So from here we say 16 is equal to negative 5a, or a is equal to negative 5 over 16. Of course, yeah, I'm glad I got that. This is negative 16 over 5, not over 25. Yeah, I just copied it wrong. The math is perfect. I mean, I just copied. So this is over 5. Glad I caught that. Sorry, it's negative 16 over 5. Yeah. Right, of course this confirm it. We have negative 16 over 5. Right, that's what we have. Right. So the math is good there. I just copied it wrong from the calculator. Right, and then of course we can also do this. Now, next, if we want to solve for b, we have to choose something different than 1 and 4. But notice both of them has s minus 2. So if we want to solve for b, choose s equal to 2. Put on both sides. Those two cancel out. And we can solve for b. And then to solve for c, we're going to choose s plus 4 equal to 0. So s equal to negative 4. And then put on both sides. And then we solve for c. Of course, will be similar to what we do here. But we choose s equal to 2. And then s equal to negative 4. We should be able to solve for b and c. But of course, the reason I do this, because this way work with the more complicated. Let's say we have quadratic factor or something more complicated, repeating factor. This always work. Yeah, this works if the number is nice. When we have linear factors, then we can do this. Right. Once again, sorry that I copied that wrong, but at least we fixed that. Right. Let's look at another problem. Now, we solve this initial value problem. So first thing, of course, we take Laplace transform on both sides. So Laplace transform of second derivative is this. Now, transform of this is a little bit different. When we have the t, so that is different. What happens if we multiply t to it? Well, that is the last one. So when we multiply by t, we have to have, sorry, we didn't see that on sorry. Okay. Yeah, now you see that. Now, t to the first power, so it's going to be negative, and then derivative of the Laplace transform. Yeah. So that This is the transform of t times something. Right, multiply this out. And then we end up to this equation. Now remember what I said earlier, that if we take Laplace transform, when we solve for y of s, we have an algebraic equation. Well, not in this case. In this case, what we have is actually a differential equation, because we have derivative here. Derivative, of course, come from here, where we have the derivative. I mean, the reason we have derivative because of this part. We have to take derivative of that. Right, so y naught, y at 0 equal to 0, second derivative equal to 0, so that's all we have. And then we have negative 2. Transform of derivative is this. Now we take derivative of this. Now derivative of this, once again, this goes to 0. Derivative of this, we use the product rule, because both of them have s. So negative 2 y of s minus 2s y prime of s. Now we have the derivative. You won't see this on the test or in the homework, because this is a little advanced. So we have that. Now of course we still need to solve for y of s, and then this is the linear first order equation. So integrating factors, multiply both sides, and then integrate both sides. We have this solution. Right, now like I said, this problem is a little bit advanced compared to what we have. Now notice that the Laplace transform is equal to 0 if the function is continuous and exponential order, meaning that we want this has to be equal to 0, because I think this should be a t, sorry. So now whatever the Laplace transform is, it should not be something that, because s go to infinity, right? So whatever we do is, this cannot, whatever we have as Laplace transform cannot go to infinity. It has to be a finite number. And you see, let's say we have something like this, for example. If s goes to infinity, this one goes to 0. I mean all of them. We cannot have the Laplace transform that go to infinity. So in that case, this one, when s go to infinity, will go to infinity. So in that case, c has to be 0. So bottom line is y of s is equal to, so we choose, so y of s is also equal to 0 when s go to infinity. And finally, we find the inverse transform of this equal to 1 over 2 t squared. Right, I said this problem is a little bit advanced, because when we apply the Laplace transform, what we have is not an algebraic equation, it is a differential equation. So we have to do that. But yeah, so in the big scheme of things, what we do in this section is using Laplace transform to solve the initial value problem. Right. So we take 3 steps, take Laplace transform and to turn the equation into an algebraic equation where we solve for y of s. When we solve for that, apply the inverse Laplace transform. More likely we have to use partial fraction. And then when we have it, apply the inverse Laplace transform to get back to the function y of t. So it's not that bad. It could be extremely tedious, because what we have here is, if we know the Laplace transform and at the end the inverse Laplace transform, that's the big deal. The middle part take a lot more work, where we have to solve for the equation y sub s algebraically, and then the partial fraction also might take some time to work on the problem. But the idea is not that complicated. Laplace transform, solve for y sub s, and then inverse Laplace transform. Right. Of course, we spent 3 sections on how to find the Laplace transform and how to find the inverse Laplace transform. Right. The remaining of the chapter we study more Laplace transform, but the way we do this problem is still the same. Take Laplace transform, solve for y sub s, and then at the end apply the inverse Laplace transform to get back to the function of t. Right. And on the rare occasion where we don't have the initial condition is 0, we need to change. Right, and that is how we change the equation and the initial condition. Right, but that's all we have for this section. As always, thank you for watching, and see you in another video in differential equations.